Let's get started, back from the break. So our next speaker is Ariel Lellouch. He's a postdoctoral researcher in the Department of Geophysics at Stanford University, and he got his PhD at Tel Aviv University. So he's going to be talking about cool stuff you can do with a downhole vertical DAS fiber, specifically forge and SAFOD data. So thanks, Ariel, very much. We're going to have about 10 to 15 minutes for Q&A and discussion after Ariel's talk. So as you have questions, even throughout the talk, go ahead and put those in the text chat. Then I'll call on people, or I'll read out the questions actually. If I need clarification, I may call on you to turn on your microphone and explain more. But that's the way we'll do Q&A today in this meeting format. So thanks very much, Ariel. Take it away.
Cool. So yeah, thanks for inviting and thanks for the introduction. So yeah, there is a better and more scientific title that the organizers put in the agenda. That's at the bottom here. And I promise we'll talk about all that. But yeah, basically I want to show you cool stuff you can do with the downhole fiber. So this is all research that was done at Stanford. Lots of help and collaboration from all these people. I suppose if you've been attending the workshop, you know at least one of them. So I will start by briefly describing previous studies in the field of passive DAS. The organizers have asked me and all the other speakers to begin our presentation with a little bit of literature review, then move on to describing the differences by looking at the downhole fiber, mostly from a processing standpoint. And I will try to convince you that it can actually be very easy to work with. I'll try to show you how a relatively simple and non-restrictive set of assumptions can actually turn processing of a downhole fiber to a very easy task, much easier than a surface array. And the reason for which it's simpler than a surface array is not what you usually think about would be the cause. It doesn't have to do with the near surface attenuation, scattering, poor coupling, all these usual difficulties in the near surface. It is something more fundamental that has to do with the seismic wavefronts we care about and how we sample them. And hoping I can convince you of the usefulness and the validity of this set of assumptions, it will kind of set a framework that we can use for many different applications. We'll start by velocity model building without any active source, talk about earthquake and microseismic event detection, location, eventually magnitude estimation. And most of the examples are going to be from Forge, since Nate did a great job introducing the site and the data, so you'll be familiar with it. But I will also show a little bit of records and analysis from SAFOD, which is a DAS fiber deployed around near the San Andreas Fault, just to vary the data a little bit. And of course, eventually try to draw some conclusions about the future. So previous studies. I'm really focusing on passive DAS and kind of the applications that I talked in the previous slides. So Lee and Jan used the Brady Hot Springs data that you've also seen during this workshop to do template matching and detect earthquakes. So they had a few templates, cross-correlated the DAS records with those templates and found many more earthquakes. This is with the surface DAS array. In the oil and gas industry, people have been looking at DAS as a tool for microseismic monitoring. Mostly detection and location. Focal mechanism is still kind of an ongoing issue. It's all pretty recent, but about 2 years ago, Martin Kallenbach and others from Optasense and the collaborators basically set the stage for a PIX-based microseismic event analysis and location. Well, you basically pick the PNS arrivals, and then you can use a velocity model to locate the events. It's not always easy because of the DAS directivity. Some PICs might be missing. You might have none, or you might have both, or only one phase. But it's basically a relatively straightforward PIX-based approach. And James Verdon and others kind of extended this to a simpler version. I would say you don't have to pick every single channel. You can pick several representative parameters in the short records or just in the records, because there are no short, just the microseismic records, and use that to get kind of a simplified location. Both of these are working with deviated wells, and they both mentioned that the more complicated the geometry is, the better your location is going to be, which is not very surprising. So that was what I wanted to mention. Now let's talk about DAS in general as a downhole sensor. So I think the main reason this is becoming so popular, at least in the downhole business, is from a logistical or an economical point of view. And that is that you can use DAS in an active well. If you put the fiber outside the casing, like you can see on the image here on the right, it basically means you keep your well free. So it can be flowing, you can log it, you can do whatever you want with it. But that means the well is free and you don't need to drill a dedicated monitoring well like you have to do with conventional downhole geophones. In addition to that, fiber is a lot more resistant to temperature and pressure when you compare it to conventional tools. So you do have to pay this one-time upfront installation cost of the fiber, but once it's there, you can get much closer to the target reservoir because you can withstand the temperature and pressure, and the fiber is going to stay there for a long time, years, or if you're lucky, even decades. So it's great for long-term monitoring. You can continuously record, but you can also, come back every year or two, do a time-lapse analysis. Maybe Julia will talk about that. And for that, DAS is really convenient. Throughout the workshop, I think no need to say it again, but the wide frequency range has been mentioned a lot. I think I counted 8 orders of magnitude. And really, there's something for every type of person with DAS. You have the reservoir engineers, and you have the seismic people, and you have the acoustic. So that's another benefit. And think of the real thread in this workshop as being the high-resolution seismic wave field that DAS offers us. And this really commands an array processing mindset. So I'm a big advocate of forgetting the old ways of point-by-point, channel-by-channel processing, and instead really thinking about all of this DAS array as like one big antenna that we can use to focus seismic energy. And the way I want to try to do that is with some, probably the simplest assumptions you can make about a vertical DAS fiber. So it's very idealized. I put the DAS here in a vertical fiber. It's idealized as discrete receivers with a whatever DZ between the receivers. And there is an incoming wavefront. We'll talk about that in a little bit. This is all passive DAS, as I mentioned. So there are 3 assumptions that I'm going to be making. The first is not an assumption. It's something that's forced upon us. And that is with a single vertical fiber, you have complete azimuthal symmetry. And there's nothing you can do about it, right? DAS is a directive measurement. It measures only strain or strain rate, in this case, in the Z component. So that means that if events come from north, east, or south, they're going to look the same because the projection on the axis is going to be the same. So we basically cannot say anything about the azimuth, and the whole problem becomes 2D problem of depth and distance from the array. Now, the assumptions that we do control are 2. First, we're going to assume plane waves, basically assume that the sources that we care about are far enough from the array that when they reach us, they are approximately plane waves. And we're also going to assume that they reach the bottom of the array first. So both of these assumptions are not always true. For example, in microseismic monitoring in the oil and gas business, when the fibers go very deep, it's not true. But for Forge and SAFOD, these assumptions hold like 99% of the time. And if we use these assumptions, we can think about the simplest case, which is really like high school geophysics, if that would be a thing. Imagine we have a source directly below the array. So that source would be propagating upwards. Let's say we don't have velocity variation. So wavefronts are just going to be propagating throughout the array in a 1D fashion. And if we look at 2 adjacent receivers, let's say these 2, actually it shows these 2, the time difference of arrival of the seismic wavefronts is going to be simply the depth, this difference between these 2 arrays, these 2 points divided by the velocity, right? It's the simplest velocity analysis or velocity model building exercise you can think about. It's just divide the 2. Now, of course, we do not control the location of the sources, and they might be coming from the side. And we keep saying that the azimuth doesn't matter, but what matters is the angle of incidence relative to the vertical. And we said that if it's coming from directly below you, we see one velocity, and if it's coming from the side, you actually have to scale that velocity by a factor of cosine theta. The apparent velocity, you will see a velocity that is slightly higher than reality. If you see it coming from the side, is actually, you have to divide the velocity by cosine theta. If you think about the limit case, if it's coming directly from the side, like directly perpendicular to the array, you will see an infinite velocity, right? Because it's a plane wave, it's going to get to all receivers at the same time, and it will appear to you as an infinite velocity. So for those of you who come from an exploration background, this is exactly like a dipping reflector in the NMO equation. And the angle that matters, I want to point out, is the angle at which the wavefront reach the array. Anything that happens between the source and the array, we're kind of agnostic to it. We don't really know what's happening. It depends on the velocity structure. And we really care about the local angle of arrival at the bottom of the array. So that was a lot of theory. Let's see what it looks like in practice. I'm going to show you examples from SAFOD. So as I mentioned, SAFOD is a very interesting science project in which DAS was a very secondary, drilled all the way into the San Andreas Fault. Lots of science experiments conducted in it. But in the top part here, about 800 meters or so, there was a fiber deployed. It's an interesting story. The fiber was deployed in 2005. It actually broke at the bottom, but was still managed to be interrogated 12 years later in 2017 and record some earthquakes, which I think is pretty cool. And these are two earthquakes recorded by the SAFOD DAS array. These two are eventually coming to the array almost vertically. And we know this from the source location that we get from the USGS, plus some knowledge of the velocity model. And we can see this is time and this is depth. I think I posted this on the Slack, one of the Slack channels, to try to generate attention. So now you can see the two different earthquakes. You can see it gets to the bottom of the array first, right? This is the deepest part of the array. You can follow the first arrivals of the P all the way to the surface. You have a free surface reflection. You have the P coda events, which have the same, kind of like the same slope or the same pattern as the P, but show up later in time. At some point, you start seeing the S waves. Again, because of DAS directivity, the S waves here don't look great, but you can definitely see something which looks much slower. Those are the S waves. We have some S2P conversions like this nice event here. Of course, the S events, they have coda themselves. Everything reflects from the surface, yada, yada, yada. It's very complicated, but at least we can somehow understand what's happening. And we will use a very small portion of this data. We're just going to use the first arrival. So we're going to use the first arrival of the P and the first arrival of the S, which need a little bit of cleaning, and I don't have time to show how we cleaned it. And to build a velocity model. It's what we said earlier. You measure the travel time difference and you know more or less the depth of the receivers, because Nate showed you how to calculate that. And we can get the velocity. So we did it in two ways. One is what every normal human being would do, and that is pick the arrivals. We also tried something more automatic and fancy based on radon transform. The difference is not huge. This is the velocity profile we get. And so this is depth and this is velocity. These are the two estimated from one earthquake. And what's really nice is that it agrees almost perfectly. It's like a 2 or 3% difference with the conventional downhole geophone survey. So that's a survey in which you have to lower geophones, couple them, detonate explosives at the surface after you have permissions and whatnot. You basically like have to mobilize the well for a day or two. And you compare this to what you can get with just like one earthquake that is just happening in the San Andreas. Does show the benefit. We were also able to do ambient noise interferometry. I think it worked surprisingly well. It's the part that I didn't do in this study, so I can praise it. Zach Spicat did that. And we get, of course, it's not the same resolution because with ambient noise, you get lower frequencies, but it does seem to catch the right trend. And if you compare this to a seismic surface derived model, unsurprisingly, because there are no very clear reflectors, the surface seismic derived model is okay, it's in the right ballpark, but it definitely doesn't have the same structure. We were also able to build a shear wave velocity model that was not very available for SAFOD. You really see this structure of like velocity increasing, constant velocity increasing again. You can look at the VP-VS ratio and see that the VP-VS ratio is going to very high values in the shallower part, which is consistent with unconsolidated sediments. All of this to say that it was supposed to be like a boring compaction model, and it's not. There's a lot to look and to study just from the velocity models. So that was SAFOD. Now let's look at Forge. This should be more familiar. Just a quick reminder, there are two wells. The pink one is the stimulation well, and then it generates all these microseismic events here. And in the red well, we have monitoring. So we have both a fiber and downhole geophones. So we basically repeated this velocity analysis technique using the perforation shots, basically opening the holes in the casings before injection. We have a known calibrated source. We know its depth and we know its location. So we can use that to calibrate the P-wave velocity model. Because this source didn't generate visible shear wave, we hacked the S-wave velocity using microseismic events such as this one. You can see really beautiful P-wave arrival, shear wave arrival, and this S2P conversion that we always see converting at the granite. And these are the velocity models we got. So the DAS ones are pink and blue, and the sonic logs are black and red. Of course, the sonic logs are from the other well, or from the stimulation well, so it's not a one-to-one match, and we had to adjust them according to the depth of the granite, but it still seems to be a really good match. So that was velocity, but how can we detect events? So it's actually the exact inverse of the velocity model operator. So when we built the velocity model, we picked the arrival times, and from that we extracted the subsurface velocity. For detection, we're going to go the other way around. We have the velocity, because I showed you how you can get it, and from this velocity, we're going to predict the arrival times. And we know that these arrival times, they depend on the velocity and the angle of incidence. Because of all these, the simplifying assumptions that we can make and the 2D nature of the problem, there is only one angle that we care about, and that is the angle of incidence at the bottom of the array. So we can actually predict the arrival times as a function of the incidence angle. We don't know this angle, so we have to scan for it, but it's a single parameter scan. And the idea is that for every try of a different angle of incidence, we're going to predict the travel time curve, move the data in time, shift the traces according to this predicted curve, and then see if the events are flat. Basically, if the events are flat, it means that we have both the velocity and the angle of incidence right. And you can measure flatness in many different ways. Again, coming from an exploration background, semblance is a very obvious choice, but others can work too. What's good about this method, it's completely picking free. You don't have to pick anything, and it's good because we have huge volumes of data, and you get the angle of incidence at the bottom of the array as a byproduct. So let me show you what it looks like kind of in a movie. This is a zoom in on an earthquake recorded at Forge. This is channel number, and this is time. And I'm going to show you what the data look like after correction with travel times predicted from different angles. So this is, for example, an angle of 0, assuming the event is coming from directly below us, and you can see it's definitely wrong, right? This is not flat. There is a slope here. That means the velocity or the travel time curves do not match the field data. So I'm going to run this movie, hopefully, yeah, and see what happens at different angles. So of course, for the very low angles, you see almost no difference. That's because cosine theta is not very sensitive to low angles. But you see that when the angles start to get higher, events are significantly flatter, and then the semblance that we measure starts looking much better. And well, I don't think I can stop the movie at this point, but you could see that. I'm gonna maybe run it again. Sorry about that. Yeah, I'm gonna run it again, and around 65 or 66 degrees, you will see that the semblance is maximal. That's what we measure automatically, and you will also see that the data is as flat as it gets. It's not perfectly flat, but it's the best we could get. And the detection just amounts to applying a certain threshold in the semblance. You can estimate it from the semblance value of the noise, which you can see here, it's very low, so you have to take some statistical margins. But once you do that, you basically have an automatic detection. And of course, you do it for both P and S waves. I only showed you the P here. So, okay. This used to be my thunder slide, but then Nate showed you this already. So it's not as thunderous as before, but this is what the microseismic event looks like. And that's what we actually are going to try to detect in the next slides. So you can see the geophones in green, co-located with DAS in the background. We see the P waves, the shear waves, and again, this very nice S2P conversion, which frankly is very obvious with DAS, but just with the downhole geophones, I think you have to be a very good seismologist to see that this is a conversion. I couldn't. That doesn't say a lot because I'm not a great seismologist, but I'm just saying with DAS, it can be much, much easier. So we try to detect microseismic events in the Forge data set. And what's cool is we have a really good downhole geophone catalog. So deployed and processed by Schlumberger, like state-of-the-art industry processing, and we can compare our results. So I processed, I think this was like 24-hour window. There are about 300 events in the geophone catalog. And you can see the ones we found in DAS are marked in blue. And this is the magnitude of the event. So very clearly, DAS finds the higher magnitude events and starts like being shaky at the lower magnitude ones. And we did a magnitude completeness analysis, and we found out that DAS is complete down to minus 1.4, whereas the downhole geophones are complete down to minus 1.7. So at this point, DAS is still not as good as the downhole geophones, at least not with this processing, but it's a 0.3 difference, which is not huge. Now, I think a more fair comparison for DAS would be a surface array, right? Because we're talking about, long-term monitoring, and no one leaves downhole geophones for a very long time. So if we're talking about induced seismicity or CO2 sequestration or enhanced geothermal systems, stuff like that, what we're probably going to use for monitoring is a surface array. So this is a surface array deployed by the University of Utah seismograph stations at Forge. We have the 2 wells here and the surface arrays in blue triangles. And these are 6-time windows, which are relatively weak earthquakes. You can see for the top row, we see the events. I mean, you can see them in probably 3 stations. You see the P peaks in green and the S peaks in red. A real seismologist picked those, not myself. In the middle row, you can also see the events. It gets a little bit shakier, and at the bottom, you basically see noise. But if you look at exactly the same windows with DAS, all of a sudden you see what's happening, right? So at the top row, those are like the really good events. You can see upgoing P. You can even start seeing those faint downgoing reflections. Those are actually coming from a geological contrast, probably the water table. As the P waves go up, they reflect from the surface. We have, again, this shear wave and this S to P conversion. We have a secondary event here and here that looks weaker, so it might be like a secondary earthquake. This event, for example, you see the P to S time difference is much longer, so it means the event is coming from further away. But even if you look at the weaker ones, which here with the surface array looked like nothing, here you can actually see them, right? So you have the P waves, the S waves, P waves, and S waves. And that gives us some hint that DAS can do really well at detection compared to a surface array. So in this case, we analyzed 10 days of data, and the regional catalog contained only 4 events that were not in the microseismic catalog. And with DAS processing, we found 82. I will say that from those 82, only 5 came from template matching, and 77 came from this like travel time prediction analysis. So we did try template matching, but in our case, it did not add too much. I would also say that if you go back to the surface data with the DAS timings, you can actually visually see 16 events. So it's not as bad as the 4 that came up in routine processing, but it's still not as good as DAS. Having said that, template matching usually works great for surface array, and I know some people are working on that, so the surface array results might get a lot better, but at least compared to routine processing, DAS seems to be doing better. Yeah, I tried to do some magnitude completeness analysis. It's a little bit hard because we don't have the magnitude for the DAS event, so we have to rely on our own DAS magnitude estimation, and there are not a lot of events, so I don't want to like overinterpret this, but we are probably better by about an order of magnitude in DAS compared to a surface array. Maybe it's half an order, but we're still doing much better than a surface array. And we can also do event location. I keep repeating that, but we cannot get the azimuth, which is a pain. But as I said, during the detection, we get the angle of incidence at the bottom of the array. So like a thought experiment is you have the angle at the bottom of the array, you shoot a ray from the bottom with that angle, and you know the event has to be somewhere along that ray. Now, if the velocity in the subsurface, you assume it constant, then this ray is going to be a straight line. If not, it's going to follow the velocity model. And then you take the S2P time to map the event or to locate the event along that ray. And we did that, comparing this case to the geophone derived catalog. And in this 2D degenerate plane, the difference between DAS and geophone locations is in the, I don't know, tens of meters at most. This is really down to the exact velocity model you use, or even the datum and the channel location. So practically they're as good as geophones, only that they don't have the azimuth. You can also do magnitude. I'm really running out of time, so I'll run over this quickly. Try to compare the geophone magnitude estimation in this axis versus DAS magnitude in this axis. Ideally, they would follow the black line. That would be a 1-to-1 ratio. It's not quite there yet, but the difference is not huge, and given the fact that we only have a single component and the instrument response is not as well calibrated as for geophones, it's a pretty good result, and it gives us trust that we can estimate magnitude from DAS, at least for the set of microseismic events. And to try to kind of wrap all of this up, looking at a downhole fiber, I hope I convinced you that it's useful for several things. First, velocity model building, in which you don't need an active source. In terms of detection, for now, it seems that downhole geophones are doing a little bit better than DAS. But this experiment is really like the worst case comparison for DAS, because the benefits of DAS is that you can get to places where you cannot have geophones. And in this case, you have both in the same dedicated special monitoring well going exactly at the same depth. So it's probably like the worst case comparison for DAS. And even so, we are within 0.3 magnitude, which is not a huge difference. DAS clearly outperforms the surface array, at least like with routine processing, around the difference of magnitude 1, maybe half. You can get decent location, of course, with this 2D limitation and magnitude estimation. And I think realistically, more complex geometries. So like multiple fibers or multiple wells or deviated wells, or a combination of downhole and surface array, like the study from the cryosphere in the lightning talks by Sarah showed today. You can probably resolve the azimuthal symmetry and get a complete location. I think taking all of this into account, DAS is a very strong candidate for long-term monitoring, geothermal or EGS, more importantly, CO2 sequestration, other applications, of course. But I think, it's a DAS workshop, so we are all super thrilled and excited by DAS. But I think at this point, it can still be really complemented and gain a lot from conventional receivers. You don't need so many, but if you can get, if you can get azimuth from a few stations, you basically solve the location problem. So maybe integration between the spatial continuity and the nice highest resolution wavefield of DAS with some specific, really well calibrated instrument response 3 components, can probably, the two together can give you a very nice result. And with that, I will take questions, but I also have a question for you. And the question is, what is this event? So this is depth and this is time. And by the end of the Q&A, I will reveal what this event, what we think this event is. So while you listen to other people's questions and you want to think, I don't know, you can think about it. That's it.
Cool. Thank you very much, Ariel.
Sure.
So I'll go ahead and just summarize a few of the questions here. We got a few questions early on about the installation type. So I'll read you a few. From Mark, please confirm for a downhole deployment, the fiber is outside the casing. And then from Chao Yi, does the fiber need a protective cover when installed on the outside of the casing? And from Martin, does it make a difference whether or not the borehole fiber is cemented to the casing? If so, could it be used to measure the quality of the cement job? And Rob left a comment that the fiber can be deployed outside the casing or inside, typically either as a wireline or production tubing. So I don't know if you could comment for SAFOD on those.
Yeah. So I was focused on outside casing because wireline deployments are a little bit tricky and they're probably not good for long-term monitoring. So lots of good questions. The story is that this was installed in 2005 at Forge, and it was installed outside between the casing and the cementing. And so at the time that this was deployed, they were using it as like a single total strain meter. And I think no one was really thinking about that at this point. So it makes a lot of difference if the fiber is outside the casing or inside the casing, especially if the well is full with fluid. In this case, it's not. And we didn't see too much ringing and too much tube waves, I think because the well was outside the casing. The coupling is a lot better when it's outside the casing. And in this case, it was indeed outside casing. Now, if you want more details on the installation, I refer you to the older SAFOD papers. There was one in scientific drilling that really describes how exactly the fiber was installed and coupled, and with lots of engineering details. But for me, I treated it just as outside casing, straight vertical fiber.
Thanks. So there were also a couple of questions about just getting the data itself. So of course we know the Forge data is accessible. How about the SAFOD data? Can you comment on where you got that?
Yes, so as far as I know, the acquisition was funded, or at least I got it from Bill Ellsworth. So we definitely have the data at Stanford. I don't know if it's like hosted anywhere else, but if you're interested, I mean, I uploaded all the earthquakes that we found in SAFOD, because we also ran a detection algorithm in SAFOD, which I didn't show the results of, but we found like something like 25 earthquakes, and I uploaded all of them to my GitHub page with the catalog. So it's not everything, and I'm sure you want to like retry and do better than myself and find more earthquakes. It's not very hard to do, but if you somewhere to get started is look at those earthquakes and see if that you can read the data properly and so forth. And I would say just contact me and I see what we can work out. I mean, we have the data up to this day, we can access it. So. Yeah.
Sounds good. I didn't realize you had put that in your GitHub, so we'll have to add that to the public DAS data document. So.
I think I did it a couple of days ago, but it's just like the bottom of the list.
Oh, okay, thanks.
Sure.
So one of the other questions on, it was how is the first arrival of P wave picked? I think that was asked right before you went into how to do the semblance calculation. Any other details you want to add
so
there?
Picking, I mean, so for the velocity model building, you can either pick it, you know, using conventional ways, STA, LTA, with some manual corrections. We found out that an automatic slant stack approach, which basically means you try to automatically fit different linear velocities to portions of the array. So you take a portion of the array, let's say 100 meters or 150 meters, and you try to give it like a best linear fit that maximizes semblance or some other coherency measure. And we found that this works a lot better than picks, because picks you can always like jump one phase and then it gets shaky and then you smooth it and then it's a little bit dirty. So we ended up getting better results with the slant stack, and especially for the shear waves, which are very dirty. Let me see if I can go back to it. But yeah, so you see the shear waves are really, really dirty. So if you try to pick on the raw data, chances are very slim. So we ended up using this slant stack approach and to get more reliable results. If you're interested, you can find all the details in this paper that I found, that was published last year, showing how to do it. But, yeah.
So on the semblance calculation, there's a question from Matthias. What is the time bandwidth product used for the semblance calculation? That is window length and the frequency used.
Yeah, so it's a very good question. And of course, you know, the devil is in the details. So what we did is we look at, you know, kind of like the representative events we have, and we try to get like half a wavelength of that in time. So I would say, I think it was something like 10 samples. So it's about, let's say like 10 milliseconds window, something like that. You basically have to catch like the coherent part of the wavefield. You can take half a wavefield, you can take a full wavefield, half a wavelength or full wavelength, but something like that. If the central frequency of your events is about 100 hertz, or let's say the maximum frequency is 100 hertz that you can rely on, then you use a 10 milliseconds and you're fine. It's kind of like rule of thumb calculations. It's not something like tailor-made. You just do a few tests, pick something, and it works. I mean, it might have some difference on the edges, but it's usually fine.
So I'm going to skip one and come back, but next question is, could you tell if you bandpass DAS earthquake data compared to geophone, in particular on slide 18 for Forge?
Okay, yeah. It should be moving there. It's very slow. Okay. Oops, yeah, sorry about that. So if I bandpass,
it's not totally clear to me if there's other details. I don't know, Tuan, if you can type into the chat, if you want to clarify that. I'm going to go ahead and move on to another question, which is, have you presented any analysis with the Forge team? Like, have you collaborated with the Forge team on this? I think people wonder about how do we use these open data sets?
while people have attended the workshop, you can just pull the data using the wonderful notebooks made by the organizers. I mean, Chris Pankow was really helpful in the beginning, and she introduced me to this data set. And she helped me a little bit with when I had questions about the geometry. But basically, you can do this on your own.
Great. So then I guess we have time for just one more question from Adam Begg. The 0.3 magnitude unit jump for MC, does that relate to a higher noise floor for this DAS processing workflow?
So yeah, that's always a great question. So I think eventually, the thing is that if you look on a channel by channel comparison, geophones do a lot better than DAS. So I think the main difference is that eventually the sensor for downhole geophones is just better if you look at the single sensor. So we try to kind of like squeeze everything we can from the fact that we have this spatial continuity and we have this array processing approach, but still in the very basic form of the measurement, geophones can listen to quieter stuff. And to me, I think that's the difference. And of course, that has to do with the exact fiber you use and the coupling and the casing and where exactly all the installation details that are very important. But I still think that at this point, and this DAS data was with an engineered fiber, by the way, I still think at this point, on a point-by-point comparison, geophones still do a lot better. And I think that's the reason for this difference.
Yeah, and even your data processing mattered a lot. So
yeah,
I think we're out of time on questions. We're going to move on to the next speaker, but would you be willing to answer some more questions just in the text chat?
Yeah, sure. I'm around. You can text me privately, whatever you want.
Great. Thanks very much, Ariel.